The latest version of ProtoTwin comes with a wide range of exciting features, including a new product, a new component, and various improvements to scripting. So let's dive right in. ProtoTwin Motion is our brand new product. Motion was designed for simple physics-based animation of mechanisms with basic sequential control. The mechanisms you see here are just some examples of the kind of things you can build with ProtoTwin Motion. You will be able to animate mechanisms like this one in just a matter of minutes. The new sequence component is ideal for creating models like this one, where the control logic is very simple and you don't need to write a single line of code. In our first example, I'll be demonstrating how the sequence component can be used to control a simple bolt and ester mechanism. I'll first go ahead and add the component to the main entity. We now need to configure the I/O for the component. I'll first create two variables. For the first variable, I'll give it the name sensor. The second variable, called screws, will be an output signal that is used to turn the screws. We now need to create a direct connection between the state of the distance sensor and the sensor signal we just created. We also need to create a direct I/O connection between the screw signal and the state of the screws component that will be used to turn the screws. Now that the I/O configuration is complete, we can begin by adding operations to the sequence. For the first operation, we'll add a set signal operation to set the screw signal to true. Next, we'll add an await signal operation, which will pause execution of the sequence until the sensor is blocked. After the sensor is blocked, we want to stop turning the screws, so we'll use another set signal operation, but this time set the screw signal to false. The bowl will now be dropped onto the conveyor belt, so we want to use another await signal operation to wait until the sensor is cleared. Finally, we'll pause for 1.5 seconds. This pause is important to ensure there is no bowl underneath the screws before we cycle the sequence and turn the screws back on. When we run the simulation, you will see that the current operation being executed is highlighted in green. The sequence component makes it very easy to test basic control logic like this one. It can help you tune parameters, such as the time interval of the pause operation. Although it's not a PLC program, it's still very useful to quickly prototype and rapidly iterate on your models. The process for creating any model in ProtoTwin always begins by importing the CAD for your machine into the simulation environment. In our next example, I'll demonstrate how our AI Assistant Torq can help you set up and control your machine in ProtoTwin by simulating a 3-axis gantry model entirely from scratch. To interact with our assistant, you can either enter your query using the search bar at the top of the viewport or click the button at the bottom of the toolbar to open the assistant pane. You can now ask Torq any question you like. I'll first ask Torq to advise me how to configure the joints and motors for the 3-axis gantry I just imported. Okay, Torq has given us a bunch of recommendations, so let's read through each of them individually. It's first telling us to switch to edit mode and select the entity for the first axis. Then it tells us to add a physics component to that entity with a prismatic joint and to configure the axis direction for the prismatic joint with the base property left empty. We then need to repeat this for the second axis, but this time Torq is telling us to set the base property to the entity for the first axis, and similarly for the third axis, but this time setting the base to the second axis entity. Since we want to drive the joints, Torq is also telling us to click the Add button next to the motor property, which will create a motor component and bind a motor for each joint. Finally, Torq recommends we run the simulation after adding each joint and motor to test the model incrementally. We first need to swap to edit mode and then select the entity for the first axis, just as Torq recommends we do. In the inspector, we then need to add a physics component and create a prismatic joint. Remember, Torq told us to configure the axis and click the Add button to create a motor that's bound to the joint. We need to repeat this process for the second joint. But this time, remember that Torq told us to set the base to the entity for the first axis. The base property we configured here ensures that the second axis moves relative to the first axis. The process is the same for the third axis. Fortunately, the default axis direction is already configured correctly. Remember, Torq told us to set the base to the second axis entity so that the third axis moves relative to the second axis. With the model setup complete, we can now run the simulation to test the joints by setting some target positions for the motors. Although we didn't follow Torq's advice by testing incrementally after adding each joint and motor, for more complex machines, incremental testing is highly recommended, since it can highlight the exact cause of an issue with your design, which may be difficult to detect without incremental testing. We expect our assistant to be very helpful for new users who aren't very familiar with simulation tools like ProtoTwin. If we open the script editor and then open the assistant pane, we can also query Torq to write more advanced scripted control logic for arbitrary machines. I'll ask Torq to create a scripted component to control the 3-axis gantry. I would like all axes to be driven simultaneously. The target positions should be specified through the inspector, and there should be a 1-second pause between each motor movement. You can press Ctrl-Enter to quickly send your message. Torq will then go ahead and create the component for you. Torq gives us a very quick brief about the component and includes the code. A gantry controller component was created with 3 public motor handle properties, an array of targets, and a pause duration. The component iterates over each target in the array and uses the sequence class with the wait-all instruction to move all axes in parallel, followed by a 1-second pause. We now need to add the gantry controller component to the main entity and then configure each of the axes. Recall that the targets were specified as a vec3 array. I'll now go ahead and add some target positions to the array and configure the values. With all the parameters configured, we can test our model again by running the simulation. While this example was fairly simple, it's worth noting that Torq can create more complex machine logic, as well as robot programs and tools that enable programmatic modification to a model at design time. In our next example, I've already gone ahead and asked Torq to create a robot program for us that picks up a bunch of cubes from the same location and arranges the cubes in a grid. The program references the manual creator component, responsible for duplicating the cube, and the suction gripper component, which enables the robot to pick up the cube. I told Torq the robot should approach the pick position and drop position by 0.1 meters. At the end of the program, the robot should also return to its home position by moving each joint to 0. Looking at the code, Torq created properties for the width, depth, and height of the grid, the cube size, and the padding offset, just as we specified. The sequence class was used again, with the approach offset correctly configured to be 0.1 meters above the cube. Torq decided to create a nested for loop for the grid, calculating the X, Y, and Z offsets, followed by the drop frame and approach frame, that is used as part of the robot controller component API. Torq decided to call the trigger function on the manual creator to create the cube before moving to pick it up. The robot controller component API is used to execute a bunch of joint moves and linear moves. The state of the suction gripper is set to true to pick up the cube, then the robot moves to the drop position and sets the state to false to drop the cube. The servo move instruction then moves all the joints back to 0 at the end of the program. We can now add the grid stack program Torq created to the entity for the robot. I need to configure the pick target and drop target entities, including all other properties. We'll make the grid 3 by 3 by 3. The cube size is 6 centimeters, and for the padding offset, we'll use 2 millimeters. Finally, I need to reference our script in the call script instruction on the main program of the robot controller component. Once again, we can run the simulation to test our program. Notice how the robot always approaches the pick position and drop position, displayed by the green spheres, from 0.1 meters above the spheres, just like we specified in our query. It's also worth noting that Torq paid attention to our query by making the drop position at the center of the grid. One final thing to note here is that ProtoTwin's robot controller component is a general solver, meaning the program Torq created can be used to control any robot. Of course, assuming that the reach of the robot is sufficient and there are enough degrees of freedom to perform the movements. Recall that at the end of the program, the robot is instructed to move back to its home position by setting the target position of all motors to 0. The script editor in ProtoTwin also supports autocompletion when writing code. I'll demonstrate some common use cases of where autocompletion might be helpful. I'll first write a comment to specify the component should reference a sensor and conveyor motor as properties. You can press Tab to confirm the changes, which will also automatically import the types. I'll now add another comment that specifies that I want to turn the conveyor motor off when the sensor's blocked. The code subscribes to when the state of the sensor changes. It first checks that the state of the sensor is true, then sets the state of the conveyor motor to false. Also included in the release of this version is the new package manager. In the template dialog, I'll first select the type as package, then click the add button to create the required files. The package.json file defines the package name, version, description, and a list of dependencies. When publishing a package, the name of your package must be prefixed by the name of your organization, which you can create through our main website. The README file describes the contents of the package along with any pertinent documentation. The index.ts file exports all the types, including any components and tools, that should be available to users upon installing the package. I'll now ask Torq to create a simple vibratory feeder component, which will vibrate the entity kinematically to transport parts resting on its surface. The component created seems to have included all the properties we specified in our query, which is very promising. I'll now go ahead and copy the code and paste it into the index.ts file. Torq has correctly used decorators by giving the component an icon, and the axis property is the local feature decorator, which allows the user to configure the property using feature selection. The start position and the time are both stored as private properties on the class. Torq then calculates the transport offset and up offset by scaling the direction vectors by the oscillation value multiplied by the amplitude, and then adjusts the position of the entity appropriately. When you're ready, you can right-click on the package.json file and then select the Publish Package option to publish your package. Packages enable you to reuse scripts in other models you make. You can open the package manager at the top right of the script editor and then browse through all the publicly available packages. You can click the button to the right of the version dropdown to install a package into your existing model. The package manager will automatically create or modify the package.json file when installing, uninstalling, or updating packages. I'll now select the feeder entity and then add the vibratory feeder component included in the package we just installed to the entity. Fortunately, the default values for the transport direction, up direction, and frequency are correct here. We just need to modify the amplitudes. Once again, we'll run the simulation to test the vibratory step feeder component. We've also included a bunch of packages with the release of this version, such as a zone deleter component, an airgun component, a suction gripper zone component, and various other tools that can help you create models in ProtoTwin.